Good afternoon. Thank you very much for tuning into my channel. Today I will be discussing Kirchhoff's law, so just bear with me. So here we go. Kirchhoff's circuit laws. Kirchhoff's laws are two equalities that deal with the current and potential difference, commonly known as voltage, in the lumped element model of electrical circuits. They were first described in 1845 by German physicist Gustav Kirchhoff. This generalized the work of George Ohm and preceded the work of James Clerk Maxwell. Widely used in electrical engineering, they are also called Kirchhoff's rules or simply Kirchhoff's laws. These laws can be applied in time and frequency domains and form the basis for network analysis. Both of Kirchhoff's laws can be understood as corollaries of Maxwell's equations in the low frequency limit. They are accurate for DC circuits and for AC circuits at frequencies where the wavelengths of electromagnetic radiation are very large compared to the circuits. Kirchhoff's current law, KCL. This law is also called Kirchhoff's first law, Kirchhoff's point rule, or Kirchhoff's junction rule, or nodal rule. This law states that for any node, junction, in an electrical circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node, or equivalently, the algebraic sum of currents in a network of conductors meeting at a point is 0. Recalling that current is a signed, positive or negative, quantity reflecting direction towards or away from a node, this principle can be succinctly stated as thus. Where n is the total number of branches with currents flowing towards or away from the node. The law is based on the conservation of charge, where the charge, measured in coulombs, is the product of the current in amperes, and the time in seconds. If the net charge in a region is constant, the KCL will hold on the boundaries of the region. This means that KCL relies on the fact that the net charge in the wires and components is constant. Uses. A matrix version of Kirchhoff's current law is the basis of most circuit simulation software, such as SPICE. Kirchhoff's current law is used with Ohm's law to perform nodal analysis. KCL is applicable to any lumped network, irrespective of the nature of the network, whether unilateral or bilateral, active or passive, linear or nonlinear. Kirchhoff's voltage law, KVL. This law is also called Kirchhoff's second law, Kirchhoff's loop or mesh rule, and Kirchhoff's second rule. This law states that the directed sum of the potential differences, voltages, around any closed loop is 0. Similarly to KCL, it can be stated as thus. Here, N is the total number of voltages measured. Generalization. In the low frequency limit, the voltage drop around any loop is 0. This includes imaginary loops arranged arbitrarily in space, not limited to the loops delineated by the circuit elements and conductors. In the low frequency limit, this is a corollary of Faraday's law of induction, which is one of Maxwell's equations. This has practical applications in situations involving static electricity. Limitations. KCl and KVL both depend on the lumped element model being applicable to the circuit in question. When the model is not applicable, the laws do not apply. KCl and KVL result from the assumptions of the lumped element model. KCl is dependent on the assumption that the net charge in a wire, junction, or lumped component is constant. Whenever the electrical field between parts of the circuit is non-negligible, such as when two wires are capacitively coupled, this may not be the case. This occurs in high-frequency AC circuits, where the lumped element model is no longer applicable. For example, in a transmission line, the charge density in the conductor will constantly be oscillating. On the other hand, KVL relies on the fact that the action of time-varying magnetic fields are confined to individual components such as inductors. In reality, the induced electric field produced by an inductor is not confined, but the leaked fields are often negligible. Modeling real circuits with lumped elements. The lumped element approximation for a circuit is accurate at low enough frequencies. At higher frequencies, leaked fluxes and varying charge densities in conductors become significant. To an extent, it is possible to still model such circuits using parasitic components. If frequencies are too high, it may be more appropriate to simulate the fields directly using the finite element modeling or other techniques. The model circuits so that KVL and KCl can still be used. It's important to understand the distinction between physical circuit elements and the ideal lumped elements. For example, a wire is not an ideal conductor. Unlike an ideal conductor, wires can inductively and capacitively couple to each other and to themselves, and have a finite propagation delay. Real conductors can be modeled in terms of lumped elements by considering parasitic capacitances distributed between the conductors to model capacitance coupling, a parasitic mutual inductances to model inductive coupling. Wires also have some self-inductance, which is the reason that decoupling capacitors are necessary. And here's an example. Assume an electric network consisting of 2 voltage sources and 3 resistors. I'll read that again. Assuming an electric network consisting of 2 voltage sources and 3 resistors. So according to the first law, we have thus. The second law applies to the closed circuit, and so on and so forth, and you can read the rest.